Bonjour à tous, bienvenue au séminaire du vendredi de l'IAP. Welcome everyone to this weekly colloquium. Today it's a real pleasure to receive Camille Bonvin talking. Camille is a cosmologist. She's well known to the French cosmology community. She received her PhD from Geneva University in 2008. She did it under the supervision of Roos Dürer. And then you moved to not far away, to IPHT Saclay with Francis Bernardo. Then you joined Cambridge in the UK for 4 years at Dept and at the Kavli Institute. And then you were a fellow at CERN for 2 years. And then you settled into Geneva since 2016. Camille is a specialist of large-scale structure. In particular, she studies general relativistic effects on large scales, but also nonlinear physics on small scales. And she's also a specialist of primordial magnetic fields and their impact on the CMB. So today it's a pleasure to have her talking for about 15 minutes plus questions about GR effects on large-scale structures. So floor is yours.
So thank you very much. Thank you for the invitation. It's really a pleasure to be here. So today, indeed, I wanted to talk about the large-scale structure of the universe and more precisely about a subtle effect, which is the distortion of time, that leaves a small impact on the large-scale structure. So what I want to do in this talk is first to discuss with you how this distortion of time impacts our observation. And then I want to discuss a little bit why it is interesting to measure this effect in the large-scale structure, what we can learn from this effect about our cosmological model. And I will argue that this effect is very important if we want to test the theory of gravity on large scales, and especially if we want to distinguish between a theory of gravity which is different from general relativity and interaction that would act in the dark sector, so additional interaction acting just on dark matter. And then I will also discuss how well we can measure this effect with future surveys. So this is an effect which is small, meaning that with current data, it is not detectable yet. But you will see we can actually design methods such that in the future, with the coming generation of survey like DESI, Euclid, and the square kilometer array, we will be able to detect this effect. So let me start by discussing how this distortion of time impacts our observation. So we'll focus today on the distribution of galaxies. So if we receive a map of galaxy like this one from SDSS, where the observer is here and all the points represent a galaxy that has been detected, what we usually do to analyze this map is to split them in redshift bins and solid angles. So we pixelize the map and then we count how many galaxies we have in each of these pixels. And so we construct the fluctuation in the number of galaxies, which I call here delta, as the number of galaxies that we have in a given pixel minus the mean number and divided by the mean number. So this delta is something that we can directly extract from observations. And so what we want to do is to have a theoretical modeling for this observable such that we can then use it to test our cosmological model. And so the simplest modeling that we could think of is simply to say, the galaxy follow the distribution of the matter. In the places where I have more matter in the universe, I will form more galaxies than in the places where I have less matter. So this observable delta should be directly proportional to this small delta, which is just the fluctuation in the distribution of matter. And B here is the bias that relates the luminous matter to the total matter in the universe. But this model is not very accurate. It's an approximation of what we observe. And the reason why it's just an approximation is because we never observe directly the galaxies exactly where they are. What we are able to measure from these galaxies is the redshift that we have. So we look at the spectrum of the galaxy and we see how it is shifted to the red. And then we observe also the direction of the incoming photon, the direction from which the photon reach our telescope. And from that, we reconstruct the position of the galaxies in the sky. Now, if we would live in a universe that would be perfectly homogeneous, so where the matter would be perfectly homogeneously distributed between the galaxies and us, then we could directly reconstruct the true position of the galaxies. Because in a homogeneous universe, we have a direct link between the redshift that we measure and the distance of the galaxy. The further away the galaxy is, the larger the redshift is. And also, in a homogeneous universe, light propagates on a straight line. So if we know the direction of the incoming photons, we know where the galaxy is. However, we know that we do not live in a universe which is perfectly homogeneous, and this will impact the trajectory of light from the source to the observer. And because of that, we will have a change between the observable, redshift and angular direction, and the true position of the galaxy. So in particular, in a universe with inhomogeneities, we have a different relation between the redshift and the distance. The redshift is itself affected by fluctuation, by inhomogeneities in the universe. And also light does not propagate on straight line, meaning that from the direction of the incoming photon, we do not recover the position of the source. And so this means that the structure that we see on a map like this one do not directly reflect the underlying true distribution of galaxies, because the galaxies, as we observe them, are shifted radially and transversally with respect to their true position. And of course, if we want to use this map to test the model of cosmology, we need to know this distortion, because if not, we would make a mistake in the interpretation of the results. And so we can do that. We can calculate this observable delta accounting for all the distortion that we have. We need, of course, a model for our universe. So with my collaborators, we did this calculation in the following metric. So here A is the scale factor describing the expansion of the universe, and psi and phi are the two gravitational potential describing fluctuation in the geometry due to the inhomogeneous distribution of matter. And so in this metric, we can calculate the propagation of light. They follow null geodesic. And then we can reconstruct the perturbation in the redshift, in the angular direction, and compute what we are observing. And here is what we found. So here you see that the first term here was our naive guess saying the distribution of galaxies simply follow the distribution of the matter. And all the other terms that we have here, they are due to the fact that the coordinate system that we are observing is distorted with respect to the true position of the galaxy. So if we look at the first line, we have here this term which is called the redshift space distortion. It is sensitive to the peculiar velocity of the galaxy. That means the velocity that the galaxy have in addition to the Hubble flow, simply because they are attracted by dense region in the universe. And so this changes the observed redshift via Doppler effect, and therefore it shifts the galaxy on the map. Then in the second line, we have the effect of gravitational lensing, which distorts the trajectory of light, so changes the angular position of the galaxy, and therefore changes the number of galaxies that we detect per solid angle. So this lensing term is proportional to the sum of the two gravitational potential, because it's both the spatial and the temporal distortion that change the trajectory of light. And as you see, it is integrated from the source to the observer. And then we have these last three lines that have actually been called relativistic effects in the literature, simply because they come from a relativistic treatment of the propagation of light in our universe. And you see that this relativistic effect depends on the velocity of the galaxy and on the two gravitational potential as well. Some of the terms, some of the contributions are local, so they depend on the value of the velocity and the potential at the position of the galaxies, and other terms are integrated along the line of sight, so they depend on what happens in between the galaxy and the observer. So these expressions really describe what we are observing in the linear regime, but it is actually not the expression that is used at the moment to analyze current data. What people are using is simply the sum of these two terms, density and redshift space distortion. And they completely neglect the other terms simply because in the regime probed by current survey, the other terms are strongly subdominant. So it's a good approximation to take only the first line here. But future survey will observe much wider part of the sky. They will go up to much larger redshift. And so for this future survey, the other terms may be important. So for example, gravitational lensing will be important when we go to high redshift because the effect accumulates along the line of sight. So for Daisy, Euclid, and the square kilometer array, this term becomes relevant. And this relativistic effect will also be relevant for this future survey that observe wide part of the sky with a very large number density of galaxies. And so what I want to do now is first to discuss how we can use this expression to test the theory of gravity in our universe. And second, to see if these relativistic effects that have never been detected yet, if they are useful to test the theory of gravity, if they contain additional information with respect to density and redshift space distortion that have already been measured. And yes, so F-evol, yeah, let me go back. So F-evol and S are two parameters that depend on the population of galaxies. So S is what is called the magnification bias. So it tells you how the luminosity, the slope of the luminosity function. And it enters there because it changes, because this relativistic effect change actually the brightness of a galaxy. And so some galaxy that you would not observe can suddenly make it into your sample because they are magnified by the velocity of the galaxy. And how many of these galaxies enter in your sample depends on the slope of your luminosity function. And F-evol encodes the evolution of the galaxy with redshift. Okay. So how the galaxy, so if there would be no merger of galaxy, the number density of galaxy would simply go like 1 over the volume. They would be diluted by the expansion of the universe. But if you have mergers of galaxy, for example, this can differ from that. And this relativistic effect, since they change the distance with respect to you, they change also at which time in the universe, you measure the distribution of galaxies. And so if you have merger, this can actually induce a perturbation in delta. So are these relativistic effects useful? The answer is yes, they are actually useful. And the term which is particularly useful to test the theory of gravity is this term here, which is proportional to the distortion of time in the metric psi. Okay, so let me now describe a little bit what I mean by testing gravity. So the reason why we want to test gravity, one of the reasons why we want to test gravity is because we have observed that the expansion of the universe is accelerating and we don't know what is the source of this acceleration. So it could either be a dark energy component, with the simplest model being the cosmological constant, but it could also be due to a theory of gravity that would behave in a different way than general relativity at large scale. And so this theory of gravity would drive the acceleration of the universe. And so if it is the second solution, which is the correct one, then we expect to see other signatures of this theory of gravity, different from general relativity, in the large scale structure, in the observation. And so the way to describe this test of gravity is the following. So we focus at late time, meaning after the CMB and actually after radiation becomes subdominant. And then, so over the range of redshift where we have observation, and we want to test gravity over this range. And so in the linear regime, we can actually describe our universe with 4 quantities. So 2 quantities that describe the content of the universe, so delta, which is the fluctuation in the density, and V, which is the peculiar velocity of the galaxies, our universe. And then we have these 2 fields, phi and psi, that encode the distortion in the geometry. Now, if we are in the lambda CDM model, then these fields are not independent from each other. They are linked by Einstein and conservation equation. So we have, for example, the Poisson equation, which tells us how matter distorts the spatial geometry of the universe. At late time, we have in general relativity that the 2 gravitational potentials are the same. And then we have the continuity equation, which tells us how a flow of particles change the local density. And we have the Euler equation, which tells us how matter falls into the gravitational potential psi. So this is in lambda CDM, but now if we want to go beyond lambda CDM and test the theory of gravity, then what we have actually differences in the relation between these different fields. So if we change the theory of gravity, typically we change Poisson equation, and we can have a difference between the two gravitational potential that is called anisotropic stress. And also, if we change the cold dark matter model, then we can have a change in the continuity and Euler equation, because the dark matter can interact with other components in the universe, exchange energy, and exchange momentum. And so if we want to test our lambda CDM model to see if we have deviations from that, what we would like to do is to measure these 4 different fields, compare them, and see if the relations are in agreement with the one predicted in the lambda CDM model. Now, the problem is that with the data that we have at the moment, we cannot test these 4 relations independently, simply because we have actually only 3 measurements of these 4 quantities. What we are able to measure with current survey is the density of galaxy and the velocity from the distribution of galaxy, and I will describe a bit more later how we can do that. And the other thing that we can measure is the sum of the 2 gravitational potential from gravitational lensing, from the distortion of light. And so the problem is that now we cannot test these 4 relations with these 3 measurements of the 4 fields. We need to make some assumption, and this actually limits our ability to discriminate between different models. And so let me give you an example of that. So suppose that I want to distinguish a model where gravity is modified with the goal to explain the accelerated expansion of the universe, from a completely different model where gravity is given by general relativity, but I have interaction in the dark matter sector, non-gravitational interaction in this sector. So these 2 models are fundamentally completely different. And so if I look at the equation in the first one, where I modified gravity, I can actually encode this modification into 2 new parameters, eta, that describe the relation between the 2 fields, and mu, that describe the relation between the gravitational potential and delta. In general relativity, these 2 functions are equal to 1. If I go beyond general relativity, they can be whatever. But then, if I change the theory of gravity, typically I do not change Euler equation, because I do not change the conservation equation in my theory of gravity. Then in this second model, I am in general relativity, so I have my standard link between phi and psi and my standard Poisson equation. But if I have additional interaction acting on dark matter, I will change Euler equation. I will change the way dark matter falls into a gravitational potential, because it will not be only due to gravity, but also to these other interactions of dark matter with, for example, dark energy, or with dark photons, or with itself. And so typically, we can encode this modification into Euler equation into 2 parameters, theta and gamma. So theta is a friction term acting on dark matter, and gamma is what we call a fifth force, an additional force acting on dark matter. And so I want to use my cosmological data to distinguish between these 2 scenarios. So what I can do is to combine this equation into an evolution equation for the matter, because with my large-scale structure, I can see how the matter cluster in my universe as a function of time. And so I obtained these 2 equations. And if you look at these 2 equations, you see that they are actually very similar to each other. What happens in both cases is that the way structure grows is modified here by mu and here by gamma. So I have an effective gravitational constant, which is different from the Newton's constant. So here it is different due to the change in Poisson equation, and here it is different due to the fifth force acting on dark matter. Now you see that the 2 cases are slightly different, because in the first case, gravity affects all matter in a different way, whereas in this second case, it's just the dark matter that feels the fifth force. So I have here this parameter x, which encodes the fraction of dark matter that I have in my universe. But this does not help me to distinguish the 2 scenarios, because since I don't know the amplitude of gamma and mu, I cannot actually use that to distinguish the 2 scenarios. Then you also see that in this second case, I have this friction term, which is not present in the first one. But this friction term, first, in many models, it turns out to be negligible. And even in the model where it is not negligible, it is itself strongly degenerated with the fifth force. And so in practice, I cannot use that to distinguish the 2 scenarios. And so this means that if I'm just looking at the data from redshift space distortion, which actually encodes how the structure are growing as a function of time, then I'm not able to distinguish between these two scenarios. I will see in both cases an enhanced growth of the structure. But if we go back to the equation, we see that there is something which is fundamentally different in these two scenarios. In the first one, I have a difference between the two gravitational potential. In the second one, they are exactly the same. And so if I can measure the link between the two, if I can measure the anisotropic stress, these will give me a way to distinguish between the two models. And so people have called a measurement of eta different from one a smoking gun for modified gravity, because it's really an indication that gravity is modified in our universe. And so this is measuring this eta is actually one of the main goals of large-scale structure survey. So this is completely true, but the problem is that with the data that we have at the moment, we cannot do this test properly. Simply because what we measure is the sum of the two gravitational potential via lensing, and then the velocity from redshift space distortion. And the way people do the test is in the following way. So they measure the velocity, they assume that Euler's equation is valid, and they use that to infer psi. And then they compare psi with phi plus psi to see if there is a difference. And here you see that if we live in a model where gravity is modified, the test works perfectly well. From the velocity, we can really infer psi, compare it with phi plus psi, and see if we have a deviation. But the problem is that if there are additional interaction in the dark sector, this test doesn't work anymore, because we would measure the velocity, use Euler equation to infer psi, but by doing that, we would not infer the true distortion of time. We would infer an effective one, which is where psi is multiplied by 1 plus gamma. And so then when we would compare this effective potential with the true phi plus psi, we would say, there is a difference between the two, so gravity is modified. But in reality, it's not the case. It's just that we have assumed a wrong equation, an equation which is not valid in our universe, to perform our test. So it means that with the data that we have at the moment, measuring an eta different from one would be extremely interesting, but it would not be a smoking gun for modified gravity. It can be there either if gravity is modified or if we have interaction in the dark sector. And so for those of you who are familiar with the measurement from the dark energy survey, here is how they perform the test at the moment. So they combine these two equations to relate phi plus psi to the density. And you see that the relation is given by this capital sigma, which is just a combination of mu and eta. And then they assume a time evolution for this function, because they don't have enough constraining power to actually test that at each redshift. And they constrain the parameters sigma 0 and mu 0, which is the deviation from 1 today. And so if you look at the data from the dark energy, first from redshift space distortion, here in green, you see that with redshift space distortion, we constrain the growth of structure, so they constrain mu. And then with the data from the dark energy survey, that are the blue one here, they constrain these parameters sigma, because they are sensitive to phi plus psi. And by combining the two, they obtain the contour here in purple. And so they have constraint on mu and sigma from this data. And if instead of using the dark energy survey to measure the lensing, you use the CMB, you obtain the red contour and then the black contour here. And so now this test works perfectly well if we want really to test gravity. But you see that if we have interaction in the dark sector, the test would fail, because with the growth of structure, we would not measure the true mu. We would measure an effective one, which is affected by the fifth force. Whereas with the lensing, we would measure the true sigma, which is related to the true mu here, because lensing does not care if dark matter is affected by interactions. And so when we compare, when we do this plot here, we would compare something which depends on the true mu with something which depends on a mu effective. So we would infer an eta which is different from one, even if it's not the case in reality. So it seems that we are a bit stuck with the data and that we cannot distinguish these two scenarios. But actually, luckily, thanks to this additional term that contribute to our observation, we will be able to do that with future data because delta here depends, you see, on psi. And this is the true psi independently of what dark matter is doing. So if we can measure this effect here, we would measure the true gravitational potential. We compare that with the lensing. And if we see a difference, then we would really be able to say gravity has been modified. Now, you see that the problem is that this term is just one among all these other terms. So if we want to use specifically this term to test the theory of gravity, we need a way to isolate it from the other terms. And we can actually do that by looking at the correlation function. So once we have measured delta in different pixels in the sky, what we usually do to compress information is to look at the correlation function, so to measure the product of delta at 2 different points, average over all possible pair of galaxies that I have in my survey. Now, if my observable delta would only be due to the fluctuation of the matter, this correlation function would be very simple because it would only depend on the separation between the pair. It would decrease when the separation increases, but it would not depend on the orientation of the pair with respect to the observer. It's the same for a pair which is transverse or a pair which is radial with respect to the observer. Now, we know that redshift space distortion breaks the isotropy of the correlation function. So I remind you, redshift space distortion is this term here, which depends on the component of the velocity along the direction of propagation. And so redshift space distortion will actually change the apparent radial distance between 2 galaxies because it impacts the redshift, but it has no impact on the angular separation between the galaxies. It does not shift the galaxy transversally, it only shifts them radially. And so because of this term, it means that the correlation function depends not only on this separation d, but also on the angle that the pair is making with respect to the direction of observation. And this is actually something which is very useful because it gives us a way to separate density from the velocity. So in the 90s already, Kaiser and Hamilton computed the form of the correlation function, including redshift space distortion, and they found that the dependence in this angle beta is actually very simple. There is an isotropic part plus a quadrupole, so proportional to the Legendre polynomial of degree 2 of the cos of this angle, and an hexadecapole here. And so what is very interesting is that now, from this data, we can actually perform 3 different measurements. We can simply correlate pairs of galaxies, average over all orientations, and with that, we would measure the isotropic part, the monopole, and get rid of the other parts because they are averaged out. We could also take the same correlation, multiply by the Legendre polynomial of degree 2, and then integrate average over all pairs. And with that, we would extract the amplitude of the quadrupole and get rid of the other because they are orthogonal to a quadrupole. And finally, we can also weight by P4 and measure the amplitude of the hexadecapole. And the reason why this is very interesting is because these 3 different quantities depends on different combination of the density and the velocity. So if we measure the 3, we can actually use that to reconstruct what is the density of galaxy and what is the peculiar velocity. And this has been done with a lot of success during the past 10 years by survey like SDSS, BOSS, WiggleZ, eBOSS, and very recently also by DAISY. Okay, so this is for the standard term, the analysis that people have already done. Now, what about the relativistic effect and the distortion of time? So the relativistic effect, they break something else. They break the symmetry of the correlation function. And by that, I mean that if I pick up a pixel in my sky, I correlate it with another pixel behind or in front, I don't have the same amplitude of the correlation. Now, you see immediately that if all my pixels, all my galaxies are the same, I can actually not measure such a breaking of symmetry because by construction, my correlation function do not care of the position of the galaxy. So I can interchange the pixel and I should obtain the same. So it means that the antisymmetric part will vanish. But what I can do is to take my population of galaxy and then simply split it into 2 populations, a bright population containing all galaxies brighter than some threshold and a faint population. And then I can look at the cross-correlation between the bright and the faint. And because of the relativistic effect, in particular because of the gravitational redshift term, which is this contribution here, proportional to the distortion of time, I will have something which is not symmetric. So it seems a bit strange, but we can actually understand intuitively where this breaking of symmetry comes from by looking at this very simple toy model here, where I have an observer who looks in a given direction, and he detects 3 galaxies, one behind the other, 2 faint ones around a bright one. And now let me assume in this toy model that the bright galaxy sits at the bottom of a gravitational potential. This is typically what happens in our universe. The brightest objects tend to be at the center of big structures. And then I have my 2 faint galaxies a bit higher up in the gravitational potential. Now, the effect of the distortion of time is actually through what is called gravitational redshift. So it simply means that the photons emitted by this galaxy has to climb out of the potential. So its energy is shifted, meaning that it acquires an additional shift to the red in the spectrum. And because we use the redshift to infer the distance, this galaxy would appear a bit further away than it is in reality when we look in redshift space. Then I'm looking at this galaxy here in front of the bright one. The light also has to climb out of the potential, but the climb is a bit smaller. So there is also an effect of gravitational redshift, but of smaller amplitude. And then if I look at the faint galaxy behind the bright one, here on purpose, I have chosen a situation which is perfectly symmetrical. And so these 2 galaxies are in the same level in the potential, meaning that this one experiences exactly the same redshift as this one. And so now if I look at the separation between the galaxies in redshift space, you see that the galaxy behind the bright one is now closer to the bright galaxy. The separation is given by D1. And the galaxies in front of the bright one is now further away from the bright galaxy. So these 2 distances are different. And because the correlation cares about the separation, it means that the amplitude of the correlation will be different for the faint behind than for the faint in front. Now, of course, this situation is totally idealistic. In reality, I don't have all bright galaxies living exactly at the center of a perfectly symmetrical gravitational potential, but it describes actually quite well what happens once we average over all pairs of galaxies. So with my colleagues, what we did is, without making any of these assumptions, we simply looked at the cross-correlation between bright and faint galaxies to see what is the signal that comes out of this gravitational redshift term. And we found that we have actually a behavior in cos beta, so a dipolar modulation in the amplitude of the faint around the bright one. And so it changes sign when we go from behind to in front of the bright one. And this is very interesting because now it gives us a way to isolate this effect. What we have to do is simply to correlate bright and faint, multiply by cos beta, average over all pairs. By doing that, we would amplitude of this dipolar modulation, and we would get rid of the other terms because the other terms do not generate a dipole. They generate a monopole, quadrupole, and hexadecapole. So it gives us a way to target the effect we are interested in. And actually, to be more precise, when we fit for a dipole, we get rid of all the terms except the one in this line here. So what we measure is a combination of gravitational redshift here and Doppler effects here. But this per se is not a problem because since we have already a measurement of the velocity from the monopole, quadrupole, and hexadecapole, we can combine everything to extract this psi here. Okay, so if we want to do that, and if we want to do forecast to determine how well we can measure this distortion of time, we need to parameterize a little bit our signal. So what I will do is the following. So I will assume that at early time, before the acceleration of the universe, I recover a universe where general relativity is valid because I'm linking the deviation from general relativity to the acceleration of the universe. So if I go at high redshift, I expect to recover general relativity. And this is in agreement with the data that we have, for example, from the CMB. So it's an assumption that I'm making here to simplify my parameterization. Of course, we can also go beyond that if we want to. So with that, it means that the initial shape of the perturbation at high redshift will be completely constrained by Planck. And then at late time, over the period where we observe galaxies, then I'm saying, okay, I don't know what is the theory of gravity. I don't know what dark matter is doing. And so I let actually the evolution completely free, and I want to constrain that with my data. And then I want to compare the different fields. So if we look at how the density evolves, in general relativity, it evolves proportionally to what we call the growth function, d1, which depends only on redshift. If we go beyond general relativity or beyond cold dark matter, we have, in general, a function that can also depend on scale. So this d1 will now be a free parameter, a free function in my analysis. Then I do the same for the velocity. So in general relativity, we can look at how the velocity evolved. We find that they evolve proportionally to the same growth function multiplied by this f, which is called the growth rate, which is simply the derivative of the growth function. Now, if I want to be completely general, I replace this evolution by a function g that I will constrain with my measurements. Then I do the same for the distortion of time. In general relativity, the distortion of time, again, is proportional to this same growth. So you see that actually in lambda CDM, the evolution of all the function is linked to the growth of the density. And so if I want to be general, I replace that by a function I. And then I do the same, this time for phi plus psi, because it's a quantity that is measured with lensing. And so I let the evolution free through this function j. So I have actually 4 functions that describe the evolution of my different fields. And I want to constrain that as a function of redshift with my data. And so the first thing that I need to do is to write my observable in terms of these 4 functions. So first, let me start with the monopole, quadrupole, and hexadecapole that people have already been measuring. So if you look at this function written in terms, at this observable written in terms of the function, you see actually that there are 2 types of ingredients in the observable. There is something here which depends on the matter power spectrum at early time, and this I'm assuming that it's constrained by the CMB. And then at late time, I have actually 2 quantities that enter in this expression. I have this b hat, which is just the product of the bias times sigma 8, where sigma 8 is a parameter encoding the strength of the fluctuation in spheres of 8 megaparsec. And then I have this j hat, which is just the product of j multiplied by this ratio at z star. And actually, this is not really important for us because at z star, we assume that everything is known. So by measuring j hat, we really measure j. And just in the case where the continuity equation is valid, this j hat goes back to the standard f times sigma 8 combination that people have been measuring with the data. So what you see is that if we combine these with information from Planck, for example, so Planck will constrain this part, and these 3 measurements will constrain both the bias and this function f sigma 8. And this is what has been done with actually many surveys. So here I have collected data from all these surveys here. So you see f sigma 8 as a function of the redshift, and with measurement from all these surveys, so at different redshift. And here in black, I have also plotted the expected evolution for this f in lambda CDM. And so what you see is first that lambda CDM is quite a good fit to all these data. So there are no deviation from lambda CDM that is seen in the measurement from redshift space distortion. But what you also see is that the error bar are still pretty large. And so there is room to really measure this quantity much more precise to see if we would see some deviations. And this is the goal of survey like DAISY, Euclid, and the square kilometer. Now, what about the dipole? So the dipole can be written in this way. It contains similar ingredients as before, something which is constrained by Planck at early time, plus the function. And so now the novelty is that the dipole depends not only on g hat and b hat as before, but also on I hat, meaning on the distortion of time. And so this is the reason why these relativistic effects are so useful. They allow us to measure, in addition to the quantity that are already measured by current survey, they will allow us to measure this new function I hat. So now with current data, it's not possible to measure this function because actually the effect is too small. But we did some forecast here for the square kilometer array on how well we can measure this quantity at different moments of the history of the universe. And you see that we have a precision between 20 and 30, 40% when we go to high redshift. And if we assume a known time evolution, then we can, of course, reduce the error bar. So basically, with future data, we will be able to measure this new function as well as we are able to measure the other function, f hat, with the data that we have at the moment. And finally, the last piece is the measurement of phi plus psi, which was encoded in this function j. So to measure that, what we need is gravitational lensing, because gravitational lensing is sensitive to the sum of the two distortions. And actually, what we can easily show is that if we combine cosmic shear from background galaxies with the distribution of galaxy of lenses in front, we are actually able, we are sensitive to the sum of phi plus psi at the position of the lenses. And so by doing multiple cross-correlation, we can really measure phi plus psi at different moments of the history of the universe. And so if we look at the signal, so people in lensing usually use the angular power spectrum. So you see that this angular power spectrum directly depends on this function j hat. So with my collaborators, we use the measurement from the dark energy survey, the public data from the third year of observation, to measure this function j hat at different moments of the history of the universe. So we did measurement in the first four redshift beam of the dark energy survey. And so here you see the measurements. So the blue points here with the arrow bar are the measurement that we obtain. And here I also plot the prediction in lambda CDM for the evolution of this Weyl potential phi plus psi. And so you see that we have already with current data quite a good precision between 5 and 10%, depending on the redshift. And what you also see is that at high redshift, we are roughly in agreement with lambda CDM, but in the two first redshift beam of the dark energy survey, we are actually below the prediction from lambda CDM. So the gravitational potential seems to be actually less deep than predicted in the lambda CDM model. And here we have, so the tension is not significant. It reaches 3 sigma in this second beam and something around 2 sigma in the first beam. And so this slow growth of the potential at late time is directly linked to the so-called sigma-8 tension in the lensing data. So, you know, in the lensing data, people usually use this data to measure the clustering of the matter, which is encoded in this parameter sigma-8, and then they compare that with what you would obtain from the CMB, and they see a small discrepancy between them, which is called the sigma-8 tension. Now, with our method, we were able to actually identify that this sigma-8 tension comes from the fact that the potential is a bit less deep in the first two beams of the dark energy survey. Now, of course, the tension is not significant enough to really conclude anything from that. We need more data. And so what we are trying to do now is to prepare the analysis with Euclid to measure the evolution of phi plus psi better with smaller error bars and also over a wider range of redshift. Okay, so this was for the dark energy survey. We also did forecast for LSST, and there we saw that we can actually reduce a lot the uncertainty, and we can reach a sub% level precision over a very wide range of redshift. And for Euclid, we are doing the forecast now, and it should be something similar at the end of the 6 years of observation of Euclid. Okay. And so now, once we will have this data, we will be able to measure directly the relation between the two potentials. We measure the evolution of psi and the evolution of phi plus psi. We just take the ratio to see if they are the same or not. And so this is the forecast that we have. You see that we will be able to measure a difference of the order of 10, 20% between the two gravitational potentials. And if we see a difference from eta is equal to 1, this would really be a smoking gun for modified gravity. It cannot be due to non-gravitational interaction in the dark side. Okay, so before finishing, I just wanted to show you a recent result that we did with my collaborators to really see, because the original question was, can we distinguish a model where gravity is modified from a model where we have dark interaction in the dark sector? And so we did here this mock analysis where we said, okay, let's simulate a model, let's simulate data where we have a dark fifth force acting on dark matter. So actually here, dark energy coupled to dark matter with a given strength of correlation. And then we analyze this data with a model that allows both for modification of gravity and for interaction in the dark matter sector. Because when we analyze the data, we don't know actually what we find in our universe. So in principle, we should be general and allow for both. And we ask ourselves the question now, can we distinguish between the two? So here on this plot, you see the constraint that we obtain. So here, beta 2 encodes the strength of interaction of dark matter with dark energy. And here, beta 1 is just the strength of deviation from general relativity. So if we use just current measurement, meaning redshift space distortion, gravitational lensing, and CMB, we obtain here, so this is for future data. I'm saying current measurement, so it means current techniques applied to future data. Then you see that we have very tight constraint on the combination of beta 1 and beta 2. So we obtain this blue line. So the only parameters that are allowed are the ones within the blue region. So we can very well detect a deviation from lambda CDM, but you see that there is no way that we can distinguish between the two scenarios. So the fiducial model, the true model, is the star here, which is allowed by the constraint. But you see also that the data are fitted as well with a pure modification of gravity and no interaction in the dark sector. And all possible combinations in between are, of course, also allowed. Now, if I add this new gravitational redshift effect, you see I obtain the red contour. And so you see that now I exclude a pure modification of gravity. So my data do not allow anymore for a pure modification of gravity. They are saying there is an interaction in the dark sector. Now, of course, we still have all this region which is allowed because of the uncertainty in the measurement, but then we could use Occam's razor and say, oh, it's very probably a universe where there is an additional interaction in the dark matter sector and not modification of gravity on top, because this would be more complicated than just a dark matter interaction. And the reason why now we are able to isolate the true model is really because we combine measurement from gravitational redshift that measure this quantity with measurement of the velocity. And so we can really test a deviation between the two quantities and really see in the data there is something which does not fit Euler equation. So we isolate this modification here. Okay, so this is all I wanted to say. Let me just briefly summarize the message of this talk. So I hope I convinced you that these relativistic effects in galaxy clustering are actually very useful to test gravity in a model-independent way. And in particular, the effect of gravitational redshift is essential if we want to distinguish modification of gravity from interaction in the dark sector. To isolate this effect, we need actually to look for a dipole in the cross-correlation of bright and faint galaxies. So we don't need new data. We just need the data that we have, splitting the galaxies into two populations and fitting for a dipole. And then with this, we can measure the anisotropic stress and also test the validity of the Euler equation. So we can really distinguish between the two types of scenario. So I'll stop here. Thank you.
Questions, comments?
Thank you very much for the talk. I have a question. You talked about the growth factor and its dependence on K, on the mode. There is also a growth rate, which can be parameterized for modified gravity and other possibilities. Have you looked at that? To if there is, more information in the growth rate and how it can be
if it depends on K, you are meaning, if the growth rate depends on K?
Yes, it depends on K, but also it has additional information. It depends on multiple parameters, and we can parameterize it for different models.
Yeah.
And it is an additional information that it can be, especially with the new data, in the future data, it can be extracted, and I don't know how much the information in the growth rate overlap with the delta Z and other parameters that you have shown here.
Yeah, so the idea is that of this measurement is that they are model independent. So the idea is to really measure the growth rate without assuming any model. And then indeed, as you say, you can actually use this measurement. Let me show them. So those are the measurement of the growth rate. Here I have compared with the lambda CDM model, but in principle, you can compare with any model you want, right? And you can constrain the part. So if you have a particular model, then you can just look at how the evolution of the growth rate behaves in this model, and then use all these measurements to constrain these parameters.
Another, short question, but it is something very, very well known. How do you distinguish between delta Z due to gravity, variation of gravity, and baryonic effect? Because it is really at the smaller scales, distant scales, therefore.
Yeah. So I think this is very difficult indeed. So here I have focused on large scales where we expect that the impact of baryons is negligible. Then if you want to have more information, indeed by going to smaller scales, you can gain a lot of information, so reduce your error bar. But as you say, you need to really know what baryons are doing. So what people are doing at the moment is actually different things. So to use, for example, hydrodynamical simulation to learn actually what is happening with the baryons, and then to try from that to extract emulators that would tell you actually how to encode the impact of baryons in some parameters that you would then let free in your analysis and constrained with the data to try actually to not bias your measurement. But it's really something which is delicate, and so I think we should adopt the two strategy. One which is to say, okay, we don't understand what is happening, so let's stay at large scale where we can be robust. And then to say, okay, let's try to go to smaller and smaller scales and see if we have
problem. The problem is that at larger scale, the effect of delta Z is very small. Huh? This is the problem.
The effect of
at larger scales, the effect of very small effect of lensing, if you like, or gravitational effects, is small.
Yeah. So the more nonlinear you go, indeed, the better your signal to noise is for this measurement. And so of course, it's. I mean, you also have to try and go there, but be a bit careful.
Yeah, I have a naive question from a poor observer's point of view. If you look at this slide or the one on the dark energy survey, what is the size of the error bar? Is it 1 sigma or is it 3 sigma? It makes a big difference.
1 sigma, it was not.
Yeah, so even in the dark energy survey at 1 sigma, you are not completely incompatible with the prediction, you know, because 3 sigma would fit in.
Yeah, we are 3 sigma away. We don't claim that we are completely, we have a small tension, a mild tension of 3 sigma. And from that, we cannot conclude anything. We just need more data. So that's why we are doing the thing with Euclid. But we could, with Euclid, of course, completely go back to lambda CDM. Yeah.
It is not clear to me what is the distinction you are making between a modified gravity theory and a modified dark energy theory, because after all, the fields which modify the dark energy, what modifies the dark energy?
Dark matter.
Or dark matter, yeah. You could consider that these are new fields that belong to the gravitational sector. So what is the definition that you are making exactly? And do you impose a condition on the stress energy tensor of the extra field, whatever?
Yes, so if you want, so I agree, the distinction is a bit arbitrary, but for example, if you have only self-interaction in the dark matter sector, then I wouldn't call that a modification of gravity. So if gravity couples in the standard way to baryons, it doesn't change. So Poisson equation, the anisotropic stress is the same, but you just have an additional force within the dark matter particle. This is what I would call dark interaction. Or if your dark matter interacts, for example, with dark radiation, so another dark sector, you wouldn't touch the gravity sector, but just the dark matter one. So the baryons would really behave in the normal way. Then you can also have theories where you modify gravity and you break the weak equivalence principle. So it means that your gravitational field, your scalar field, for example, couples in a different way to baryons and to dark matter. And so in this case, you would have actually everything together. You modify the theory of gravity and you modify also, you have also additional interaction in the dark matter sector, which this time are gravitational. And so where the case that I presented is really, when I call dark matter interaction, is really the case where I don't touch the gravitational sector.
A question, comment? And I have one about faint and bright galaxies. About faint and bright galaxies and how to extract the dipole. There was the initial toy model, the naive one from theories, which I understood because it's simple based on gravitational potential. But then when you go to the real world with faint and bright galaxy, it seems to be very different than just the location and the gravitational potential. It depends on magnitude, intrinsic
yes,
stuff related to galaxies.
So what really matters to extract the signal is the different bias between the bright and the faint. So if you want, in the end, the signal, maybe if I go back to the expression for delta that I had. Here, yeah. So the antisymmetric part comes from T's density correlated with T's term. And the antisymmetry actually comes from the fact that you have here just one radial derivative of psi. And so you see that when you correlate to delta at two different points, you measure T's times T's for the first galaxy times T's one for the second one, plus T's for the first galaxy multiplied by that for the second one. And because they are antisymmetric, what remains is actually the bias minus the bias, and it goes to 0. And so to extract this antisymmetry, you need galaxies that are that have a different bias, so that the signal would be proportional to the bias of the bright minus the bias of the faints multiplied by this correlation. So the math is that, but then I think the intuition is the correct one, is to say the bright galaxy, they are actually more closer to the center of a gravitational potential. They have a larger bias. They are closer to the center of the gravitational potential. And so when you correlate that with something which is not at the bottom, you obtain something, something remains.
Thank you. Well, if there's no other question or comment, let's thank our speaker again.
Okay.